Hello. In the previous video, we discussed delta U equals Q plus W. Delta U is internal energy, Q is heat, plus W, which is work. But in this video, we are going to take a closer look at work itself and a thermodynamic value called enthalpy. There's a specific type of work called pressure-volume work, and we're going to start there. It's a type of work, pressure dash volume. And the visual that you should have when thinking about work via pressure and volume is a piston setup. So you have this little chamber, and in terms of a car engine, you have multiple chambers. And each of those chambers has a piston. They could go up and down. And in this case, we'll go down. Okay. That piston is connected to a crankshaft, like this. Okay, so as this goes up and down, you're going to turn some gears. So what's causing this? What's causing this work? What's causing the piston to go down is a gas combusting. A little explosion. The gas expands, pushes the piston down, and you start to crank the shaft. So that is doing work, and in this case, work is done against an external pressure. External pressure. So we have all the components. We have work, we have an expanding volume, and that work is being done against an external pressure. When you think about the setup, work is being expended, energy is being expended, and do you remember the sign for work in that case? The sign for work would be negative. W is negative, work being done by the system. Okay, so now we're set up for the equation that I want to talk about. W equals negative P, and sometimes the textbook will have external, EXT, sometimes it won't, and there's a change in volume. And this is an important equation, so let's put it in a box. What's interesting about this equation, though, is that at this point, you may be used to energy in joules or kilojoules or even calories. But, work is in the unit, has energy units, but pressure is typically, the SI unit is atmospheres, and volume is going to be liters. So this work is going to be in what's called a liters atmosphere unit. And there is a conversion. The conversion is 1 liter atmosphere equals 101.3 joules. Okay, so there's your conversion if you want to convert liters atmospheres into joules. Okay, but what if work is done under constant volume? So we have an if situation. If work is done at constant volume, you see how delta V becomes 0 because there's no change, and then pressure external times 0 is 0. So in this case, work also equals 0. When that is the case, what do we have? We have that delta U equals Q plus W. Do you remember that equation? But now W equals 0. So therefore is the symbol with 3 dots. Delta U internal energy equals just Q. Okay. And most often you would write Q V equals internal energy. Internal energy. And again, this one is important. And what does that little v stand for? That little v stands for constant volume. So we're looking at a situation that has constant volume. But I'm going to tell you now that this is actually pretty rare. This is not the typical situation that we're looking at. So this is not usual, I guess is what we could say. It's not usual. Why? Because most reactions, abbreviation for reactions, I'm going to use RxN, are open to the air. And are usually constant pressure, atmospheric pressure to be specific, and we're not really constraining the reaction to a volume. Constant pressure, whatever the atmospheric pressure may be in the lab, not constant volume. So while this is important to know, the Q, the heat, right, at a constant volume is equal to the internal energy. In most reactions, we're not going to have this situation, okay? And let me just write, so what is the equation when you have constant pressure? So we have this constant value, Q, heat. Well, the heat at constant pressure, so Q subscript P equals delta U plus P delta V. Do you know where this came from? This came from the fact that we have this one, delta U equals Q plus W, but we know that W equals negative P delta V. So when we bring this over to the other side and bring the bring the W over to the other side, that negative P external delta volume equals positive now, P external delta volume. I'll put it in green, but I'm not going to box it. Okay, we're actually going to substitute delta U, and we're going to get QP equal to something a little bit different than what we see right now. So although it's nice to know this, again, I'm going to box all the important equations. So far we only have 2. Okay, but this is at constant pressure, and like I said, we're going to use a different form of this in just a bit. But I want to switch gears, and we will revisit. Promise. Okay. I want to switch gears and talk about now our second part of this video, enthalpy. Enthalpy has a weird definition. It's not very intuitive, but it's an important value when we talk about thermochemistry and thermodynamics. Let me see if this focuses a little bit better. Okay, enthalpy. So enthalpy, and the symbol for enthalpy is H. I should put this in blue. It's a definition. H is a value okay. Right now, don't worry about why people were interested in this value where you have internal energy plus pressure and volume. Okay, they decided to call that addition enthalpy. Now all of these are called state functions. H, well, let me say U, PV, and therefore H are all state functions, which means that it doesn't matter, the value doesn't matter how you got to that state when you go from initial to final. All that matters is the change, final minus initial. Okay, no matter how you get to the initial to the final state. So these are called state functions. Right? Because we are going to start using now the delta. So next we're going to convert this equation into the change of enthalpy. And that is delta H, I'll do this in green, equals delta U plus P delta V. Now, on the previous page, recall that we have QP, that's the heat, right? The heat at constant pressure equals delta U plus P. Give me 1 second. Yep, P delta V. Oop, almost made a mistake. All right. So do you see what's happening here? If we replace this delta U plus P delta V, we get delta H equal to the heat at a constant pressure. And this is for most processes that we are going to study, because most reactions are done, again, open to air under constant pressure. This is an important equation to know. QP equals delta H. Put a little box around it. So if you're keeping track of what we're doing, we're looking at processes where there's constant volume. Again, just remember Q is heat, and the heat equals the internal energy. All of the internal energy, the change, right? No work because the volume is constant. And then contrast that to, if I could get it on the same screen, heat at constant pressure, it's equal to enthalpy. That's very useful for us. Constant pressure. And again, this is usually the case. This is usually the case for reactions studied. Okay. Because of this, you may be familiar with the term enthalpy of reaction. Enthalpy of the reaction is synonymous with heat of reaction. For most processes that we'll study, these terms are interchangeable. When you talk about the enthalpy of, for instance, an endothermic reaction, you're really talking about the heat of that reaction, the change in heat. Okay, but we got to be a little bit careful about this equation here, because usually enthalpy is in the units of kilojoules per mole. So let me put here a warning. Enthalpy and technically change in enthalpy is in kilojoules per mole. So we are going to augment this equation right here, and we're going to say delta H equals, let's put delta H of the reaction equals the heat of the reaction divided by moles equals the heat of the reaction. And now we're not going to put P anymore. We're going to assume that it's at constant pressure divided by the moles. This is the one we should box. Because not here, but in later problems, we're going to do stoichiometry, and you're going to be given a certain number of moles, like 0.728 moles. What is the heat of the reaction? What is the delta H? If the delta H of a reaction is, I don't know, 72 kilojoules per mole, right? Per mole. What gets a little bit hairy is when your coefficients are not all 1, okay? Because this mole actually means per mole of reactant that has 1 as a coefficient. And I'll explain that in just a bit. That has 1 as coefficient. When one of the reactants has 1, you think of it as when you have 1 mole of that reactant, you have 1 mole of that reaction. Let me give you an example. Here's an example where we have 2 reactants. One has 1 mole, and the other reactant has 2 moles. What is this? You remember this as a combustion reaction. You're adding oxygen, and your byproducts, or not your byproducts, but your products are going to be carbon dioxide plus water, and it's balanced over here. It should be balanced, okay? And what if we are given that delta H of the reaction equals negative 890.4 kilojoules per mole. So there's a couple things. The first thing is, what can we conclude? We can conclude that this is the enthalpy of the reaction. We could think of it as the heat of reaction. So this is, you could use the technical term or the real term enthalpy, or you could use the term heat. So enthalpy of reaction, the same as heat of reaction. Now, do you remember if we're going to really think of this as a Q, right? Do you remember what Q means when it's negative? It means that it is releasing heat. So this negative sign, it means that it's exothermic. Okay, so whether Q is negative or delta H is negative, you are going to think of that reaction as exothermic, releasing heat. So there's heat on this side of the reaction, and you could put that if you want, plus heat. It's actually plus 890.4 kilojoules of heat if you have a mole of methane. So this number right here is technically per mole, not of the oxygen, because that has a coefficient of 2, but it's per mole of CH4. All right, and because carbon dioxide has 1 as a coefficient, you could even think of it as per mole of CO2 produced. You see how that's going to change things when we start doing problems that involve stoichiometry? What if I said that we have over here 82 millimoles of O2? Well, if this is per kilojoule per mole of methane, then we got to figure out how many moles of methane we have, okay, by using mole ratio conversion. Right. I know it's a little bit complicated. This is the problem, or this is the analysis that you'll have to make a lot in this unit, equating some enthalpy of reaction to a chemical formula or a chemical equation. Okay, we'll do more of this in later videos. But now, yep, why don't you practice? And I have one problem already printed out for us. And we're going back to pressure volume work right there. Okay, and if you need a reminder, whoops, don't look at that. Well, let's take a look at the question first before we jump to any equations. To inflate a balloon, you must do pressure volume work. So we just came out and said it. On the surroundings, your work is going to push against an external pressure. If you inflate a balloon from a volume of 0.100 liters to 1.85 liters, okay, volume's getting bigger, against an external pressure of 1 atmosphere, how much work is done but in joules? What you can do, I have the answer all printed out and the work shown. Why don't you pause the video and try this problem, and when you think you have an answer, go ahead and unpause and we could take a look at what I did. All right, the first thing I would do is that I would recognize that I have to get work. So here's work, question mark. And it has to be, I have to remind myself that the answer better be in big J, joules. I look at what I'm given, and I recall an equation that I can start populating with values, and that's the the pressure volume work equation. Plug in your numbers. All right, we are solving for W, and just remember that since this is in atmospheres and this is in liters, we do have an energy unit called liters atmospheres, but we are going to do the conversion and cancel out the liters atmospheres to get joules. Does it make sense that it's negative? Okay, I know that there's a negative sign here, but it's negative because we are, or not we, but the system is doing work. It's exerting energy to do this work, to expand the balloon against some pressure to make it larger. All right. In the next couple of videos, we are going to start looking at now enthalpy, and the majority of this unit is delta H, and how to manipulate it, how to calculate it, and what it actually means for the chemical reaction.